So first up, we'll look at understanding the site and what the tree needs. So all sites are not equal and give us different challenges and opportunities. Understanding your site and what the limitations are is the foundation to stacking your productivity gains. For example, you may have a site that's low in soil nutrients that is limiting the site, or there may be no nutrient limitation, as perhaps the site was a fertile farm. Or you may have a needle disease that is impacting on your needle retention. To stack up productivity, the dominant site limitation must be addressed first, with sight of what the next set will be. To understand a site, it's important to know the soil. The soil is one key driver of forest productivity. It is where the tree gets its water and nutrients from, and it's the structure in which the roots grow and hold the tree up. We have looked at soil productivity drivers. We did this through a national analysis using the New Zealand Planted Forest Inventory to understand soil chemical productivity drivers. We found that forests planted on farms will on average have 18% higher productivity. The key soil properties that were related to the improved productivity were soil carbon to nitrogen ratio and soil organic matter, which could be represented by soil total carbon, total nitrogen, or organic phosphorus. From this work, you can now collect a soil sample from your site and use it to predict your site's productivity. To help manage nutrients, NewBARM, a nutrient balance model, has been developed and tested for nitrogen and phosphorus. NewBARM has simple inputs of a given 300 index value for a site, silvicultural management regime, and a site fertility, which is measured through a soil sample. A general version of NewBARM is available in Forecaster, and you can use NewBARM to predict your current productivity nutrient uptake and what the gap in nutrients is to reach a target productivity. The graphed example here is from the Southern Kaingaroa Accelerated Trial. It shows the amount of nitrogen in the tree biomass and the forest floor over one rotation for the actual productivity, what you're growing there, and an aspirational target productivity, of which we picked 20% of what we had. What the model run shows is that there is a 500 kilogram per hectare nitrogen gap. This gap must come from either external inputs or through making better use of what you already got. For example, the soil actually holds 2,440 kilograms of nitrogen already, but much of that is unavailable for plant uptake. In reaching the target productivity, the site has been improved and should be able to stay at that higher level for multiple rotations. So this graph shows the same information as the previous slide, but is presented as surplus nitrogen and nitrogen that is demanded from your soil. This output from NewBARM is useful as it allows us to understand when a forest is in its highest nitrogen demand year and what amount of nitrogen is required from the soil to meet that demand. For example, first up, there is surplus nitrogen as the plants are young and unable to use all the nutrients on site. Then, as the stand grows, there is a peak nitrogen demand about 4 to 7 years as the canopy is building. As the forest grows, so too does the forest floor, which will eventually start cycling and supplying nutrients to the forest at later stages of the rotation. If at any stage the demand for nutrients is not met, there will be a loss in productivity for that site. I now want to demonstrate genotypic sensitivity due to site properties and what this means for increasing productivity through site genotype selection. Here we have 3 accelerated trials on pumice soil. that are ranked as a hard site at southern Kaingaroa, mostly due to the climate and low soil nitrogen, and a good site at Rangipo, mostly due to the fact there's a high supply of nitrogen. It was an ex-farm. And a middle site sits in amongst those two of central Kaingaroa. So here we have a graphed Rangipo, the good site, for tree DBH over a range of genotypes, and the same genotypes are shown at central Kaingaroa, the middle site. At Rangipo, the best tree is 57% better than the worst. At central Kaingaroa, the middle site, the best tree is 114% better than the worst tree. Therefore, there is much more to gain from selecting the right tree at the middle site compared to a good site. Understanding the site capital to stack productivity for the future forest management, plus puts us on the right trajectory towards maximising productivity. The next step is optimising your silviculture.